Yep.
Great. Go ahead and get started.
So, hello everybody. I'm Dmitry Revin, the maintainer of strace, and today I'll talk about a new strace feature called syscall fault injection. So, does anybody know what a strace is? Nice. So, as most of you know, a strace is a traditional diagnostic, debugging, and instructional user space utility for Linux. How traditional is 25 years old, so quite traditional. And traditionally, it's used to monitor interactions between user space process and Linux kernel. The most known are system calls and also signal deliveries, changes of process state. A strace has traditional, everything is traditional with strace. It has traditional command line interface and multiple filtering capabilities. So because the interface is traditional, it's easy to use for people who are used to this for 20-something years. And it's quite powerful because of these filtering capabilities. But last year, a strace has been extended to do something very untraditional. That is to tamper with traces by injection faults. It's so-called syscall fault injection. The current implementation is based on the work made by GSOC student of last year, Nahim Mani. I'm not sure how to pronounce his name, so I'm sorry if it's wrong. He will someday correct me. So, what is a fault injection? Just a brief recollection. It's a software testing technique used for improving test coverage, mostly of error handling paths that might otherwise rarely be followed by introducing faults. This is a nice definition from Wikipedia. Thanks to Wikipedia for this. So where do we place a strace among other fault injection tools? It's obviously software. It's runtime. Most of instrumentation tools are compile time. This is runtime. It does its work by means of syscall interposition. It's user space. Unlike many current techniques we have, it's unprivileged. And as I said, it has traditional command line interface. So now I'll show you a series of examples that hopefully will get you an idea what the syscall fault injection syntax is and what you could do with it. And I'll start with a simple program, cat from core utils, which is linked dynamically with libc, and we will see what could be done. So in the top box, you see a traditional output, and in the bottom box, something with fault injection. So let's filter all open syscalls of this trivial command, and let's file them all. What you can see here, that everything ends in dynamic linker. It tries to open its cache, it fails. It tries to open libc in predefined locations. On this architecture, there are 4 locations in this build of libc, and it fails. Nothing very, it's quite predictable. Let's do something different. Let's change error code that dynamic linker will get from default one, which is NOC's function not implemented, to something that has a different meaning for dynamic linker. As you see, it tries twice as many locations when it sees error code in the end. The error code of OpenSyscall. You can inject fault not on all invocations, but just in the first one or whatever else. So if you inject a fault just to the first invocation, you can see that dynamic linker just it does all the same. It tries libc in different locations, finds it, and everything works. But if you fail second and all subsequent invocations, what happens? Dynamic linker opens its cache and tries to open libc according to the cache. As you see, it fails. And then it tries all these predefined locations. And you can notice that it tries libc, tries to open libc at the same location it tried before. Why dynamic linker does this? Because there are different code paths and they don't know about each other. In the first path it tries to open, and in another code path it also tries to open, and it doesn't care that it's already tried this. It's not a bug, just a funny thing. Let's dynamic linker do its work and have a look at the cat itself. So the third open syscall is the syscall made by cat itself, and it looks like what you would expect from a cat. It fails and it exits with error code. Another way you can specify faults is to say how often you would to inject them. For example, you can inject them starting with third and then every second one. So you see that cat handles the situation, I would say properly. So it reports error on every case when there is an error and processes everything that's opened and exits with error code. So looks like cat works fine. And now let's have a look at something more interesting. Let's combine fault injection with path filtering. So in the top box you see a sequence of syscalls that are related to the files passed to cat, dev_num in this case. And in the bottom I will just fail each of these syscalls, so we will see how cat handles this. So the first one we've already seen, and the second one is fstat, and for some reason cat considers this as an error. It's quite an unusual thing that fstat fails, so probably it's a same thing to do is to fail everything. From another side, the fadvice syscall, it's advice. So cat is also quite right that it ignores this error. It's just an advice to kernel that cat is going to do some sequential reads. More or less the same with read. If you fail a read with a hard error, it's quite right to report it and fail. But what do you think cat will do if it sees a temporary error? Would it restart a read or would it fail? It would restart. Cat is a good program after all, and it knows that interrupted system call is a temporary error that should be restarted. So, and this is a peculiar thing. And this is when you fail close syscall that has no importance, what cat does? It just opens file, processes it, and closes it. It opens it read-only, and what's the use of reporting this as a hard error when you can't close a file opened read-only? I don't know. I would say it's a minor bug in cat, very minor, to complain and exit with error code, because the file was successfully processed from the beginning to the end. So why does it? Here you can see in brief that you can specify different fault injection expressions that would work, and in the top box. And the second box you see that a strace actually can follow descriptors. So even if cat has no idea what the file it's working with. Strace does know and can apply its filters. So it's like what you can see in the bottom box. It's a primitive, primitive access control using strace. And let's have a look at real bugs. This is a more or less famous bug in Python 3.5. It was found by the student who did this GSOC project. Python, on every invocation, needs some randomness for initialization, and when it fails to obtain this randomness, it's a fatal error, which is fine, probably, but it's not fine that it throws a segmentation fault at hexadecimal address 50. It's not good. It's a bug. Why it does this ridiculous thing? Because it addresses a method of an object which was not allocated because of lack of randomness. So hexadecimal address is just offset in a virtual table like this. Fortunately, this bug seems to be at least fixed in Python 3.6. First, they work around with it by using getRandom syscall, but I actually tried to fault getRandom and found out that it no longer faults. That's funny thing anyway. And another real bug was found with dynamic linker itself. So if you fail mprotect, you can see that dynamic linker from libc ignores error from the first mprotect error, but it treats all subsequent errors as fatal. It's quite natural to do so with all subsequent, but why it ignores the first error? It's because there are different code paths, and the only code path that exists in current libc's dynamic linker is the one that's early in its running, and it just ignores the error. And this error actually can happen, for example, because of fragmentation. And the call that's failed is the one that tries to remove access. It's prot none. So actually, some pages remains to be accessible, which are supposed not to be. So it's like it would be a minor security issue if it's not a imaginary problem, because if first mprotect call fails, it's very likely that all subsequent also fail and they are properly handled. But still, it's a bug. Now I'll try to explain you what's going on under the hood and how it's all implemented. So when traces invokes a syscall, kernel puts it in so-called syscall enter stop state. So it's completely stopped. At the same time as trace awakens, it fetches syscall number, its arguments, applies filters you've seen on all other kinds of filters as trace supports. It decides and may either skip this syscall or print something, and then it tells the kernel to go on with its tracey. Then kernel executes the syscall, and before passing control to user space, it puts traces again in a stop state. It's a slightly different state. It's called syscall exit stop. At this time, as trace awakens again, it may fetch syscall return code and arguments. It depends whether the call is filtered or not. Also, it prints at this time this return code if necessary, and tells kernel to let the tracey go on. And all this cycle repeats itself until something happens with tracey, when it exits or whatever. So taking these two parts together, you can see the sequence. And in this sequence, there are two places where a strace actually can tamper with syscall. With syscall number, with syscall arguments, with syscall return code. And this is exactly the way how syscall fault injection is implemented. So on entering syscall, a strace replaces syscall number with an invalid one, -1, and then kernel sees this invalid syscall. It's just invalid syscall, so it returns an error for the invalid syscall, which is innocuous on most architectures, but not on all of them. So you shouldn't rely on this error code. And then on exiting syscall, if instructed to replace error code, it replaces this error code with the one that was specified. So it's actually pretty simple inside. But this is not the only thing, as you can see from this slide. It's not the only thing that could be done, not just syscall fault injection, but other kinds of injections, tamperings. For example, this is some recent development, not in released strace version yet. You can inject a signal at any of these points, and current implementation, it's injected on exiting, I think. Yeah, on exiting syscall. So what would you use this signal injection for? For example, if you want to terminate program, you would probably use a different signal for this. Or if you want to dump it for the analysis by another tool like GDB. And another way you can tamper with is to replace return code of syscall with something that doesn't look like an error actually. So you can pretend that syscall completed successfully, but actually skip it. So by replacing syscall number on entering to an invalid one, this way you skip the syscall. And on exiting, you can replace return code with like 0, which for syscalls like unlink means that everything is fine. So the tracer will suppose that unlink completes successfully and the file is gone, but it's actually there. This is not as easy as it looks. As for more complicated syscalls, they have some semantics that has to be followed somehow. For example, many syscalls, when they succeed, some portions of memory are filled with some useful information by the kernel. So for them, this is not as easy. But for simple syscalls like unlink, it's work from current master. Probably I forgot to tell that this API strace is using is called ptrace. It's the same API used by, it's a traditional interface as I think about strace. So it's the same that's used by GDB. That's more or less all I would like to tell about fault injection, but I can answer your questions because some things are better answered in questions. So, by the way, the title of this talk was probably invented by the student who made this GSOC project. You can visit his GSOC page and maybe you'll get an idea what was planned in the beginning and how it's changed and compare these things. You can grab the source. Syscall fault injection is part of the recent release, which was in December, I think. So you can use it. Do you have any?
I'm kind of curious if are there testing tools you have seen that are built on top of the fault injection in strace now?
So this fault injection makes strace a testing tool, but it's quite a modern thing, so I'm not sure it's already widely used as a testing tool. I'm thinking of using strace itself for a strace test suite, because it's not easy to reproduce some faults related to ptrace system call, for example. That's so just a new way of fault injection, a new way of testing something that's otherwise would require a compile time instrumentation. It's probably the only runtime unprivileged user space fault injection tool for Linux we have now. So I think it's time to ask questions.
Okay, when you show us the cat opening that node with the block being open syscall, yeah? The cat was able to print to the screen the error that he didn't finish, but how he could print so if in theory he couldn't be able to load the linker to his memory, so the print function shouldn't be filled at the global offset label, yeah?
So which one of slides? So
So here, the cat is unable to open linker. Probably
so the question was how cat was able to complain about how cat was able to report an error if linker was unable to load libc. It's not a cat. The error diagnostics you see comes from dynamic linker. It's not a. It's still a dynamic linker at this point. So you can see the prefix is cat, but it's not a cat. It's dynamic linker who complains that it can't load libc, and that's all. Any more questions? Yes, please.
Do you know why we use an invalid syscall number to prevent syscall execution instead of some harmless syscall like get process ID? I expect that if you have some monitoring system like that in your interface, an invalid syscall number might be more alerting to that system than just calling get PID, which should have no side effects also.
First of all, I've been told, so the question is why the current implementation uses an invalid syscall number for fault injection instead of using some harmless syscall that has no side effects, so that a monitoring system like SE Linux wouldn't, or something like this, audit with it, wouldn't complain about something wrong is going on. First of all, it's not easy to find a harmless syscall. I've been told recently that getpid might fail. In current Linux kernels, getpid might fail. It's not allowed.
You are overriding the return value anyway, so I don't care what I fail.
Okay, so in theory, it's possible to invoke a getpid, I think. It's not a technical issue, but from optimization point of view, it's probably less work, you will need less syscall invocations to do this. On exiting syscall, you'll have to replace like 2 registers on some architectures, and in case of invalid syscall, you will not have to replace at least the register that contains the indication that it's an error. So it's slightly, I think it's slightly faster to use an invalid syscall, but I think it's quite a valid point. Thank you. Any more questions? No? Really? Okay. Yes, please.
Is there already something there, probably external to strace, to do random, like fuzzing stuff that randomly some syscall failed?
So the question, as I heard it, was: is there anything probably external from strace that do some random? What's a random injection? A random what?
Yeah.
So in the initial GSOC design, there was an interface to do some random injection, but later I decided that it's better done by a fuzzy driver that runs a strace. So my idea is that if you want randomness, you just do it in a driver that runs a strace and not in a strace itself. So currently this injection is predictable. There is no random injection. But it might change if somebody would suggest a plausible case how this would be used. Because currently I think it's better done in a fuzzy driver outside.
Just that the command line will get very long. I mean, if you have a real life application, the command line will have tens of thousands of things where to fail and where not to fail.
Is it a problem that the command line is long? Okay. Does anybody have any more questions? Yes, please. I'm not sure I hear anything, but I will have to repeat what you're saying, so please make it hearable, at least for me.
Not so much a question, more comments. This is really cool stuff, and it's very, very good, very, very helpful. Thank you. And pass on the thanks to the GSOC student as well.
Okay, so Steve said that it's a, well, you probably have seen it. This is like just a good words about this. I'm not going to repeat this. Thank you.
So coming up next in this room, we have a quick talk on testing web applications.
On même pas ta tablette et tout.